Spinorama is a set of speakers measurements defined by ANSI 2034 spec. ANSI is for American National Standards Institute, which is a private nonprofit organization that published some specification recommended for the industry in the United States. Spinorama information was initially developed by Dr. Floyd Toole, while he was at the National Research Council of Canada, then further pursued and refined at Harman International nearly 30 years ago. It has been adopted by ANSI as standard method of measurement for in-home loudspeakers. Spinorama consists of a series of on-axis and off-axis speaker measurements, which identify the amount of direct sound coming from the speakers to the listener, and also how much of the off-axis sound is being more widely dispersed. Importantly, Spinorama measurements can predict whether listeners will prefer a given speaker in their listening room. Spinorama ANSI spec is based on measurements of the speaker's frequency response at 70 different measurement points, starting on axis, and then at each 10-degree angle around the speaker both horizontally and vertically, as illustrated on this picture from Dr. Toole's book Sound Reproduction, the Acoustics and Psychoacoustics of Loudspeakers and Room. The measurement's reference axis is critical as this will affect the end results for the speakers. As we discussed in my earlier episode, tweeter-level measurement may not be the right reference axis, depends on the speaker's design. The ideal speaker's reference axis shall be aligned with the recommended listener sitting location, and this is typically somewhere below the tweeter level. ANSI spec clearly mentioned that any Spinorama results shall define the measurement reference axis so the consumers can understand how it was done. Data shall be referenced to an RMS input voltage of 2.83 volt at a distance of 1 meter. ANSI spec is suggesting to use the anechoic chamber to do the measurements in 2 meters distance for the far field measurements, as this will represent more closely to what the listeners will hear the sound. A Spinorama chart has 6 curves presented on it, as showed on this chart from the ANSI 2034 spec. From the top to bottom, they are: on-axis frequency response is showed as the solid curve on the top. This is the sound directly coming from the speaker front path. This is a single-point measurement which might be different from the traditional speaker's frequency response curve. The traditional frequency curve is typically the average of plus-minus 15-degree horizontal window in front of the speaker. Listening window response is showed as the dash curve second from the top. This curve is the average of 9 measurements: 0 degrees, plus or minus 10 degrees, plus or minus 20 degrees, and plus or minus 30 degrees in the horizontal plane, and plus or minus 10 degrees in the vertical plane. This is wider and including the vertical response impacts comparing to the traditional frequency response curve. The early reflections curve is showed as the third curve from the top of the chart. It is an estimate of all single bounces, or first reflections, in a typical listening room. ANSI spec defines the early reflections from 28 measurement points for floor bounces, ceiling bounces, front wall bounces, side wall bounces, and rear wall bounces from both horizontal and vertical planes. But some implementation might be using the average of only 8 responses, such as plus or minus 40 degrees, plus or minus 60 degrees, and plus or minus 80 degrees in the horizontal plane, and plus or minus 50 degrees in the vertical plane. As you might be surprised, most of the sound we are listening in a room is from the reflected sound. So this is very important curve, especially many speakers do not have good off-axis response performance. The goal is to see this early reflection curve is as close as possible to the first 2 curves mentioned above. It is well known that the human hearing system responds to direct sounds as distinct from later arriving reflected sounds, and that, among the later arriving sounds, there appears to be greater weight given to early reflections than to later reflections. The earliest reflections encounter only one room surface en route to the listener, and thus are potentially among the loudest reflections. Later reflections, commonly lumped into a descriptor such as reverberation, are much less loud because of the distance traveled, and because they have encountered several different surfaces in the room during their transit. The inverse square law attenuates sound with distance, and reflective surfaces are rarely perfectly reflective, and energy is lost. Sound power is showed as the 4th curve from the top. This is a weighted average of all 70 measurements collected horizontally and vertically. This represents all the sound emitted from the speaker that will fill your listening room. The smoother these 4 curves we mentioned so far, the better the speaker's performance will be, as the ripples or major variations on these curves will indicate some sonic issues for the speakers. The early reflection curve and the sound power curve shall be sliding down in the upper frequency range as our ears are more sensitive to them. Otherwise the speakers will most likely too bright in your listening room. The next 2 curves on the bottom are for Directivity Index as showed. Their y-axis on the chart is shifted so you shall read the bottom as 0 decibels. The higher the Directivity Index curve goes, the narrower the sound directivity angle will be at that frequency. This will translate the speakers will have more coloration due to the room reflection mismatch impacts between off-axis sound and on-axis sound. Sound power DI is defined as the difference between the listening window curve and the sound power curve. The sound power DI of 0 dB indicates omnidirectional radiation, as showed on the base frequency zone. The larger the sound power DI, the more directional the loudspeaker is, in the direction of the reference axis. The last curve on the Spinorama chart on the bottom is the early reflections directivity index. The early reflections DI is defined as the difference between the listening window curve and the early reflections curve. A DI of 0 dB is omnidirectional. A high DI number is 10 dB. As a general rule of thumb, lower DI speakers, DIs in the 5 dB to 7 dB range, will be preferred in blind listening tests. The smoother the DI curves will indicate better performance of the speakers. Now what is the Klippel, as you might have heard, for the Spinorama measurements? Klippel is a measurement equipment as showed on this picture. It is a robotic machine that can do the automatic near-field measurements in a normal room. This helps to avoid the very expensive anechoic chamber room that most people and manufacturers cannot afford to use. It uses the time delay info to filter out the room reflection impacts, so the measurements can be calculated to represent the far-field sound characteristics. It can also collect much more data than the Spinorama defined in ANSI spec. It can take the whole sphere around the speaker, with thousands, or even tens of thousands data points, and using its proprietary software to plot some sophisticated images for more detailed data analysis.